So that's the title of the talk, Roger Apéry and the threefold that Fano missed. Right? And probably all of Koskich students know what threefold Fano have missed, but maybe not so much people have any idea what Roger Apéry have to do with it, right? So how it's related to me, maybe mostly. History of 20th century by rational geometry, more generally, geometry. Yes, I won't claim any new results in mathematics, but there's some discovery in history of mathematics that I want to share with us. Yeah. So maybe I will try to put Fano in the context in a joint group with Vasily Iskovskich and one brother of one French president, probably. Katya can tell who is it. Okay, we have French people and say Henri Poincaré, Gino Fano, Vasily Iskovskich, Henri Poincaré. Yeah, so what these three people have in common? Right? They all missed more or less the same threefolds. Yeah, they're in a good company of people who missed or how some say overlooked or something the same threefolds, the same three-dimensional variety. So maybe let's start from Poincaré because he was the first one to miss something, right? And just before people write, let me share the Poincaré. Do you hear me well, right?
I think you're not sharing the screen. Yeah, now you are.
And now I am. Yeah, so here's the brother of the French president. And what do we know about him? That somewhere between end of 19th century, beginning of 20th century, he created a discipline that we know now as topology. He called this work analysis situs. And the first draft was in 1895. The last was in 1905. So he had to change some definitions and some of the conjectures, in particular one of the 7 millennium problems, so-called Poincaré conjecture. And it has an interesting story. Where was it? Poincaré. It should have worked. Yeah, sphere. Yeah, so who knows how Poincaré originally formulated his conjecture in 1900? Right, so in his work, he introduced two new concepts, fundamental group and homology. Homology was categorification of Betti numbers that were known before. And so his formulation of originally his conjecture was the idea that probably homology is such a strong invariant that it can distinguish three-dimensional manifolds. He was saying that if you have three-dimensional closed manifolds such that it has no homology, then it's a sphere. Yeah. And it took him maybe 4 years to realize that conjecture was actually wrong. Yeah, he constructed an example of three-dimensional manifold such that it's closed, homology is non-trivial, but manifold is not a sphere. And the manifold is known as Poincaré homology sphere. And I think in 1904 he had some picture. There's a Seifert textbook that has this picture. So the funny thing that this manifold, it has zero homology, but nevertheless it has non-trivial fundamental group. So then in 1904 he reformulated his conjecture, saying that fundamental group is a stronger invariant than homology, that homology is not sufficient, but fundamental group should suffice. And then, okay, 100 years later it was proven. What is this Poincaré sphere? So Poincare sphere. Ow. Is the following. We can start from a three-dimensional sphere, which we can realize as a group SU2. Yeah, it's all 2 times 2 unitary matrices with determinant value. Then if we have some subgroup G inside this group, subgroup, then we can consider quotient as U2 goes to SU2 mod G, say left or right conjugacy classes. And this quotient is a finite covering. So that's finite, this finite subgroup. Then this is finite covering, So SU2, of course, is simply connected since it's a sphere. So fundamental group of SU2 mod G equals to G. Right, and then what's the homology of this? Let's call this manifold XG, then homology of XG is the quotient of fundamental group by its commutant. Right, so it's G mod GG. So in principle, it might happen that if we have some finite subgroup inside SU2 such that this group equals its commutant, then we get manifold which has no homology, but still it's not a sphere. And this group, we know we need to consider icosahedron inside R3. And we have isometries of icosahedron inside SO3R. Right, SO3R is a quotient of SU2 by quotient by subgroup plus minus 1. So you can consider this binary icosahedral group inside SU2, and then some computation actually shows to you icosahedron group we actually positive isometries, right? So oriented isometries. This is just A5, and in the course of algebra we know that commutator of A5 is itself is trivial. For this binary icosahedron, you can do the similar computation and see it. Yeah, so this implies that X binary icosahedral group is H1 equals to 0, but pi1 not equals to 0. This is Poincare homology sphere. Yeah, so this is the manifold was discovered in 1904, but as far as I know, this nice description in terms of groups and invariants was not there, was not available. People who do invariant theory, they knew, of course, about representations and so on, but they were not contacting each other at the time. So what we can say about this? Of course, this SU2 is just a real form of PGL2 or SL2. So SU2 is a real form of SL2, and SO3R is a real form of PGL2. Yeah, and so in principle, this manifold, just we see it, it's SL2 or PGL2, this algebraic group, affine groups, So if the algebraic groups are algebraic varieties, fine varieties, they act by finite group, take the quotient, it's still algebraic variety. So in principle, this description of Poincare homology sphere, it makes clear that Poincare homology sphere is a real form, real points of some algebraic variety. So Poincare homology sphere is a locus of real points of an algebraic variety, and actually a fine variety. either SL2 or even PGL2. These are affine groups. Affine groups. Okay, so because given an affine variety, maybe you can put it to some affine space and then compactify it by some projective space, or you can abstractly think about what are its good compactifications. And the leap between this 1904 and the good compactification that was considered is 84 years. Right? So there's some in so now 1988, 1982, sorry. So it's 78 years, 1982. Two Japanese mathematicians, Mukai and Tomimura, they were classifying some subgroups, three-dimensional subgroups in Cremona groups. They were saying that classically the classification was done by Fano and Enriquez in the end of 19th century. Fano is 1899, so classification of three-dimensional algebraic subgroups in Cremona 3. And they figure out more or less this example. So how can we compactify something like this? So we can say that PGL, whatever, PGL2, or let's say SL2, it's a bit easier. SL2, SL of U, it acts on some representation, so U is whatever, K2. Some V representation. And what representations of SL2? Some symmetric power SD of U. Right, then we can say that PGL U, it acts on the projectivization of SD of U. And then if you take some point here, then we can take its orbit. Yeah, and you can look for some nice points, highest weight orbits and so on. In particular, the orbit is isomorphic to the group PGL U modulo stabilizer of P. So if you find some P such that stabilizer says binary icosahedral group, then the orbit, it naturally will be isomorphic to this quotient, right? And the closure of the orbit in this projective space will be some natural closure of this quotient. So if you find a P inside P of V such that stabilizer of P is isomorphic to icosahedral group. Here it's not binary because I already speak about PGL. I mod it out by the center. Yeah, icosahedral group, which is A5, right? Then orbit of P is isomorphic to PGL 2 modulo this icosahedral group. And then you can put it into its closure, orbit of P closure. So this is natural algebraic way to construct compactifications. And how you can do so. Again, the space V is just space of polynomials of two variables. So you look for some homogeneous polynomial such that its root, they should form an orbit. So you can look either, for example, icosahedron, it has 12 vertices on the sphere. So you can look for homogeneous polynomial whose roots are these 12 vertices. So the icosahedron, it's homogeneous polynomial of degree 12. And then its stabilizer, it will be icosahedral group. And the respective orbit of this point, it will be the Poincare homology sphere, right? So pick 12 vertices of icosahedron in S2, which is Riemann's sphere P1 of C. And then P is a polynomial in C of xy, whose roots are these vertices. Then it implies that stabilizer of P is icosahedral group, and PGLU module stabilizer of P is Poincare homology sphere. Well, I told it in terms of complexing, but of course, if you choose the right real structure, yeah, you can do it over real C. So, in particular, Poincare homology sphere is particular real locus of some affine algebraic variety, but also you can do it as real locus of a projective algebraic variety. Just in this case, the thing that we add at the infinity does not matter because our affine part was already, its real points were compact. So the thing we add, they do not have real points, they're purely imaginary. As if when you compactify a circle to a conic. Okay, so that's Poincare story. So what's fun about this Mukai Umemura? Mukai Umemura, of course, were 78 years later after Poincare. So this particular compactification, compactification is known as Mukai Umemura threefold. And most of the audience, of course, know here and had some work about it, that it is a Fano threefold. So where does it live? We want to go into projectivization of 12th power of C2. Right, so 12th power of C2 is C13, so this is P12, right? Yeah.
It's better to add one copy of C.
You want to add one copy of C, yeah? Yeah, maybe. So yeah, not a little bit better prepared. Yeah, then it will be P13. Yeah, so what's important, so this U22 so-called, it has the following properties. Its degree, the dimension, of course, is 3. Degree is 22, and it's embedded in anti-canonically minus KU into P13. As Sasha says, if you add one copy of C, then you have 13-dimensional space. You have some P12 inside. Yeah, so maybe this P12 is the infinity that you add. Sorry about this. Yeah. So what is the Fano threefold according to Fano? So if you go back to Fano, his earlier works, 1934, 1938, but even he has worked before that. He considered threefolds X inside some P G+1, such that their linear section is canonically embedded curve. So we have X inside PG+1, and inside them we have PG, and its linear section some surface, and inside this PG we have PG-1, so we have some curve. So we want this to be a canonical embedding given by KC. So this actually have to be my anti-canonical embedding, and this S will be a K3 surface. So usually Fano threefolds related to K3 surfaces of canonically embedded curves. And he kind of provided some classification of them. And Fano, by consortium, classified all Fano threefolds. Well, classical terminology, there's some prime series and secondary series of prime series. Yeah, so in modern terminology, you can say that, say, for example, they're Picard group of x, for example, equals to minus kx. Let's look for this example. Z times minus kx. So it's cyclic and generated by this guy. It's a little bit different. Yes.
Can you explain exactly how do you construct the manifold U22?
Yeah, U22 is a closure. It's a closure of an orbit of PGL2, which acts in some representation. You start for group PGL2, SL2. You just look how it acts on the space of degree 12 polynomials. In degree 12 polynomials, you choose some particular polynomial whose roots are vertices of icosahedron. Yeah, you have homogeneous polynomial of two variables, so its roots are points on a CP1. CP1 is two-dimensional sphere. You can say if you have two-dimensional sphere, then it has unique complex structure, right, such that it's CP1. You can just consider orthogonal projection. Put these 12 points and maybe project from one of them. So one will become 0, another infinity, and there will be 10 more points. You can write explicitly this 10 complex numbers. You have symmetry with respect to rotation, so it will depend some homogeneous polynomial that depends on u times v times some quadratic homogeneous polynomial of u to the 5 and v to the 5. It also appears later in Apéry's work, a little bit unrelated to this, but yeah. You can just say that you start from regular pentagon, consider its vertices, then draw the diagonals and consider the intersections of diagonals. You have 5 plus 5 points, so this is 10 points, plus 0 plus infinity, so this is 12 points. I think I'm right that this is exactly the projection of the vertices of icosahedron. But one way or another, you have this symmetric polynomial whose symmetries are icosahedral group. So you consider this point in the representation. And Sasha suggests that actually it's better to consider this representation of homogeneous polynomials and just add trivial representation. So you just, before projectivization, you can already act there. I think that I missed this point. Yeah, so consider one particular point and then take its orbit. So orbit will be quotient of PGL2 by icosahedral group, and then take closure of the orbit. Did it help?
Okay.
Yeah. So kind of construction that could be easily, relatively easy. It's a closure of an orbit of some particular thing whose stabilizer you know. And stabilizer you know just from geometry of icosahedron. Just if you know icosahedron well, then you can construct this.
Okay, thank you.
But then to check some properties that it's really smooth thing, and so on, that you need to do something. Of course, the orbit itself is smooth because it's a quotient of a group by a discrete subgroup. But what happens, this boundary divisor, it's more interesting. But people in the room, they can explain it much better, like Yuri Gennadievich or Sasha Kuznetsov. I think more or less many people here, they had at least one work about this threefold, some related threefold. So this is U22. And what's interesting about this U22, you can say it's it's the last Fano threefold that was found in a sense. So from the classification of Fano threefolds. Well, there's also those that has Betti number at least 2. So this was done by Mori and Mukai, and it's a little bit different story. Here they used minimal model program, but in principle, classification of Fano threefolds is one of the pillar stones, one of the beginnings of higher dimensional birational geometry of dimension 3 and higher. And it was, if say prime series, I think it's called prime series. It was finished. The last point was put by Mukai Umemura, U22, by Mukai Umemura from CC 1982. But in principle, construction is that simple that you don't know why it's not from 19th century or beginning of 20th, so it just happened this way. You can also describe it in terms of other geometry as all the polar decomposition of a square of quadratic equation of 3 variables. So this is also something that people certainly know this manifold, but they didn't recognize it was a Fano threefold. It was known in the end of 19th century to other community of algebraic geometers, but they kind of global properties of this, they cannot compute, it was not accessible. They know the dimension, some invariants, but not this. Okay, and inside the story, somehow what Fano wrote, right? So Fano himself told the following. So we can look for, first of all,
I didn't get the last message. So you say that U22 was actually implicitly known to somebody before 1980.
Yeah, certainly, because you can look for the following. U22 is part of a manifold which is called V22. U22 is particular case, particular point in in three-dimensional. 3 times 3 minus 1, 6 dimension. Yeah, in six-dimensional family of threefolds. And this family we usually call V22. They have some parameter, and how can we describe this? So this parameterized by genus 3 curve or plane quartic. So if you have equation of degree 4 in 3 variables, x, y, z, then you can look for all the ways how you can write this F4 as sum of linear combinations. Yeah, alpha 1 L1 to the 4 plus plus alpha n Ln to the 4. And when this number n equals to 6, you can see that variety of all this kind of representations is 6-dimensional, given a quartic, sorry, 3-dimensional variety. And if you take particular case F4 equals to x squared plus y squared plus z squared squared, yeah, so this is Mukai-Umemura. This is Poincare homology sphere, Poincare homology, or Mukai-Umemura. Mukai-Umemura, they work, of course, on complex world. So a complex world is just you take a smooth conic. There's a unique smooth conic on the plane. So you have a quadric of rank 3 of 3 variables. Take it square. Then look for all the ways how you can decompose the square, what I wrote, as sum of force powers of linear things. You look for whatever, for collection of lines, right, such that there exists such alpha. You want collection of L1, L6, such that exists alpha 1, alpha 6, such that this. Yeah. Okay. In other words, you can look for Veronese variety. You take force Veronese image of a plane, V4 of a plane, and then you look for particular point. You can realize this point in some second, in 6 seconds of the thing. So yeah, people studied this kind of stuff. They had name for it. Yeah, there are parameters here 4 and 6 and 3 variables, degree 4 and 6 of this. So there's some particular name, and yeah. So this class of just small, but people did not know that much about them. Like the main problem, people were interested, like what's dimension of this variety, because sometimes even dimension does not work as you expected. There are some defects and so on. Yeah. They did not have any tools to recognize that. Yeah, it has Betti number, Betti number 1, and that's smooth and so on. Sorry? Yeah.
Is a variety of sum of powers.
Yeah, variety of sum of powers. Yeah, VSP, and then you put some numbers. Oh, sorry, variety of sum of powers. VSP, variety of things. I just sometimes forget sums of powers. In particular, for this thing, it's clear that our group SO3, it will act. Yeah, the group SO3 is the exactly group of isometries of the conic that's transformations that preserve this quadratic form. So if my transformation preserves this quadratic form, then it preserves its square, and then it will act on the ways how you can decompose this quadratic form into forces power. So, okay. So it's in this 6-dimensional family. This family, it's modular space of genus 3 curve, modular space of plane cortex, essentially. And the point that Fano, he kind of classified Fano threefold, but he missed the whole family. Fano classified threefolds by a number, let's say h cube. So this is minus kx cube. So you can call this number 2g minus 2 because that's the degree of canonical embedded curve. Degree of canonical class of a curve is 2g minus 2. And canonical embedded curve is embedded to pg minus 1. So our threefold should be embedded to pg plus 1. So degree 2g minus 2 inside pg plus 1. So sometimes I call it 2n. So you see that n equals to g minus 1. And you can say that Fano told that n equals to 2, 3, 9. Of course, there's also example of n equals to 1, but it's not really embedded in a space. So Fano didn't consider this case. In more recent works, how Manin and Eskovskih and others define Fano threefold, they just say it's a threefold whose anti-canonical class is ample. Minus k is ample, but not necessarily very ample. Yeah, so if you look for very ample, n has to start from 2, but if it's ample, we can also do n equals to 1. This is double cover business. Yeah. And so he actually missed. So this V22 corresponds to n equals 11. So this is V22. N equals 11 or g equals to 12. And then how do we know it in Moscow? What's the continuation of the history of this mathematics? What happened before Fano and Mukai Umemura? So there was Fano. And then after Fano, so Fano, he died in 1952. And during the war, because he was of Jewish origin, he went from Italy, from Turin, where he lived all his life, to Lausanne. And he was a professor in Lausanne. Then after the war, he returned back to Turin. And still published after the wars. He has some papers in 50s, 47, in some, also in some Catholic journal published on Pope. Proceedings of Pontifical Academy of Rome, this kind of stuff. in different journals. So I'm just speaking from Catholic University and from Pontifical. It was fun. They have abstracts in Latin for these journals. Yeah, but anyway, so he died in 1952, and there was another mathematician of British origin, but very much related to Italians, whose name was Leonard Roth. And he was kind of continuing the work of the Fano, but for higher dimension, right? So he did analogous classification of varieties of index 2, but already fourfolds. It's such fourfolds, still whose section is canonically embedded curve, so it's such fourfolds whose section is a Fano threefold. So some of them you can extend, some of them you cannot extend. About this V22, I can just tell in advance, you know, you cannot extend it, neither U22, neither V22. But all the others you actually can extend, so some extensions to dimension equals to 4. And he wrote an important book, which is called Algebraic Varieties, Algebraic Threefolds, probably Algebraic Threefolds, with a special regard to rationality questions. As we know, of course, Fano, he was doing some classification of things, and he also was proving that various of the things are rational or irrational. To prove that something is irrational, well, you construct some birational map. To prove that something is irrational, you have to do something, construct some invariant. And so, birational classification. For example, Fano already figured out that you have the variety V14, so that's 2g minus 2 equals to 14. And then it turns out that it's birational to cubic threefolds. And how come claimed not rational. And the first recognized by now proof is Clemens and Griffiths, right? Griffiths. 72. But there are some other things that are rational. You have, for example, P3. It's an example of Fano threefold. Of course, it's index not 1, it's index 4, as we know, canonical class is -4 hyperplanes. We have a quadric. And there's variety B5 of index 2. Index 2 minus KB equals 2H minus KQ 3H minus KP 4H. So all of them are birational to each other, at least over complex numbers. Of course, quadrics over reals, they have different forms, rational and irrational. And there are a couple of others, right? So there's this V18 is rational, and there's some nice projections, and there are different, you know. So this also different works that Fano did, and classification actually related to classification of this birational map, what we now know is Sarkisov program. So Fano's classification is related to study of birational maps. So this is Sarkisov program by now. It's called by Miles Reed Sarkisov program. And what is classically a birational map? Well, that's something like this. You have X, and then you want to construct some rational map to somewhere. I'm not sure, to Pn. But how you construct a rational map? You consider some linear system, right? But what is a linear system? So linear system. Well, there are some complete linear systems, and there are some incomplete linear systems. You say we look for some quadrics, or whatever, passing through line, or quadrics that pass through line and doubly pass through line. They vanish twice, such that they lie in the square of an ideal generated by a line, or they lie in an ideal generated by some curve, some degree hypersurfaces passing through some configuration of curves or points, maybe that pass through a point and are singular on this point. That's what you do for. You have some different projections, projection from center Z. So this is essentially just some linear system, say DH minus Z, which means that degree D things, degree D hypersurfaces passing through containing Z. My hypersurface, say H, have to contain Z. So how you can tell it? Of course, in modern terms, we have to blow up X with center in the Z to make our map more regular. And then here we just consider DH minus E, where E is an exceptional divisor. Right? That's exactly the same as say that our thing was passing. And then, okay, this is already linear system, and we give a map to some Pn. If it's base point free, maybe still it's not base point free, then still it's not so well defined and so on. Okay, what is a double projection? Double projection. We just take DH minus 2E. That's it. So it corresponds to our equation F. It was in the square of the ideal of Z in the original terms. In terms of shifts, we take I Z square of DH, something like this. Global section of side global sections of all of DH. And so this was the method of Fano, and one of the particular examples how it works. Projection from a point does not work so well in this business. Double projection from a point works for index 2 things. Projection from a line also it's something that, so the idea maybe you do projection, then you say that here I can do some surgery, maybe I obtain some singular variety, but I can change something. So there are flops actually. So there's so Fano was doing double projection from a line, and essentially mostly using only this method, he already was able to simplify. So you project and you say, okay, now I get some other things, and I can relate what are invariants of the image here and there. So I have some map from X to its image Y. But if it's birational, I can also give it by other way around. So going from X to Y is some linear system. Going from Y to X is also some other linear system. And morally, like if X is Picard index 1, it has first, second, beta number 1, then its blow up is second Betti number 2, and this blow up of I also second Betti number 2, and between them you have some maybe flow up also, something like this. They have essentially same divisors, but maybe slightly different curves. And somehow with this method, Fano did the stuff, but we know from Iskovskih 1972 work, he was just redone by the same method as Fano did, and he figured out that Fano missed one case. So Fano missed one family. So exactly this V22 when n equals to 11. And to most of the people in Moscow, it looks that what we know, like the threefold what Fano missed was, and in the world actually, to everybody, Japan, was redone in 1972 by our advisor Vasily Iskovsky, but that's not a complete story. So why my talk is called Roger, Apéry, and Fano threefolds, and a proof that Fano missed. So now maybe I stop sharing and share Safari. Yeah, we see that Fano threefold that was missed by Poincaré, and it's essentially, as I thought, Iskovsky redone the classification, but he had some assumption that a line has normal bundle O plus O of minus 1. And it turns out that all of this Fano threefold except for Mukayo Mimura, actually line have this normal bundle, but for Mukayo Mimura, it's a little bit degenerated, O of 1 plus O of minus 2. So for this reason, somehow in the 6-dimensional family, Vasily Iskovsky missed one point that corresponds to this double conic, as I thought. And then this extra point, it was added 10 years later in 1982. And then later, of course, this classification was redone by different groups of people, by different methods, and so on and so forth. But 82 probably the first year that's considered. It's done completely, but 72 is first year which was considered where all the families were already known, all deformation classes. There was one deformation class missing. So we see that one of them a posteriori is related to Poincaré homology sphere. So here's Gino Fano, considered one of the last great Italian geometers. Who are the other great Italian geometers? Usually people put, so whom will you name? There's a holy trinity of Italian geometers, right? It's Castelnuovo, Enriquez, and Severi. Who can tell what's the difference of age between Fano and Severi and Enriquez? Okay, actually, I'll tell they're actually from the same year. So Enriquez and Fano, they just were born in exactly the same year, but for the reason that Fano was doing kind of threefold business and Enriquez more the surfaces, people sometimes think that Fano is older. So they born the same year, essentially, maybe even classmates. Fano just died also later. That's also important. You see it, he died already at 8 years old. So you see the definition of Fano variety. Here are the two. Are you seeing what I'm sharing now?
Yeah, sure.
Find that.
Fine.
Yeah, so you can look for the Wikipedia of the Fano variety, and that's the standard narrative. Yeah, that in dimension 3, there are tratata, and they were studied by Iskovskih-Manin. There are some later Iskovskih work. I thought it's 72, but it's written 77 here. Yeah. Okay, so, sorry, I made the wrote 77, 78. Yeah. And also Vasily Iskovsky, he, I think, gave a talk at ICM, but I forgot which year was this, either 78 or 82. And maybe he wasn't really there. Probably he just sent this. There was one in Warsaw, but because of Yesenin Volpin, people were not allowed to go. I forgot exactly this part of the story. And Mukayo Umemura is 82, Mori Mukayo 81. So we can say that classification of Fano threefolds was done by 82, something like this. So here are two the references to the Fano work, 32 and 42. And Leonard wrote, so that's some paper of Fano, that's his notation. 3 is dimension, 2p minus 2 is the degree. So he used p instead of g. And just the name of his paper about algebraic variety, about three-dimensional variety with canonical curve sections, right? Many names that they even copy the name of this article. So here's this British mathematician Leonard Roth. So he was born in 1904, the year that Poincaré discovered Poincaré homology sphere, died in 1968. And he was related, as I told, to Italian algebraic geometry. He lived a couple of years in Italy before coming back. So there's a classical textbook in algebraic geometry by Semple and Roth. And here's his textbook. It's written 1955, algebraic threefolds with special regards to problem of rationality. It's already after Fano died. I think he maybe first wrote it before. So in this book, he repeats classification of Fano threefolds, and I think that's where the source where Vasily Skotsky actually were looking for his sources more than papers of Fano, but that's coincides with what he explained. And so he writes also about this fourfold story. Nothing like variety of degree 22 appears there. So apparently, even in the book, which was pretending to be explaining the story, it was unknown neither to Roth nor to Fano. To Fano until his death in 52, and to Roth at least 55 and later. Okay, so now I'm coming to the main person about whom I want to speak, Roger Apéry. So you can see that he's a French mathematician of Greek origin, was born in 1916, died in 1994. During the war, he was mobilized, hospitalized, and he was Severi told him that since you're in Germany, you can visit Göttingen and something. And something interesting, of course, he's famous for proving that Z of 3 is irrational, and that was in 78 approximately. And he also, I think, went to ICM around this time to explain this thing. It's some infamous story how he announced it in France, and the proof was not first well accepted. People have precise time to digest the idea. So that's already a result in, you can say, arithmetic of the numbers. But here we can see an interesting thing that his doctoral thesis was in algebraic geometry in direction of Paul Dubreuil and Paul Garnier already after the war, after he was released, but he was still doing some classical algebraic geometry over closed fields. And so there's an interesting reference, maybe I'll share another thing now. It's an obituary written by his son, François Apéry, which is also a mathematician. He's also a mathematician, and he's my source of knowledge. So you can see that here is, that's his son already with his son. That's the young Roger Apéry at Sorbonne in 39. That's already older version being treated by his wife. So he's with Dieudonné in 70. Some funny story about this Bombieri, like Bombieri told, maybe this equation has no solutions in integers, then Apéry just wrote the solution, Bombieri told non-trivial. And by the end of his year, you can see that he was kind of intuitionist in some sense. He was dubbed intuitionist by others. He was not Bourbakist. He did not like the idea of formalism and more preferred constructive things, to do explicit constructions to those stuff. So he was invited to join Bourbakist, but refused, similar as Leray, I think. In this regard, he's similar. And for this reason, somehow he was a bit isolated from the society of French mathematicians and algebraic geometers of the time. And he gradually moved from classical algebraic geometry to number theory, passing through algebraic geometry, or say non-closed things and so on. And so the end of his career, you can say this famous proof that, which was named the proof that Euler missed. That's some pun of my title, that he proved that Z of 3 is irrational, and for Z of 2, of course, we have famous formula of Euler that Z of 2 is p squared over 6. It's not a proof that it's irrational, but still, because for p squared over 6, it was proved later that P is irrational. But all even values of zeta, they go from Euler's solution of Basel problem, or are very different. And there's the 30-year gap, 31-year gap from the first work of Apéry, from his thesis in 47 and his famous work on zeta of 3. For me, it's important because I worked last 15 years of something that I called initially Apéry class, or sometimes asymptotic class, and I have a couple of works on so-called gamma conjectures with Sergey Galkin. So these gamma conjectures, they originally were some kind of mixture, applying some ideas from Apéry's proof of rationality of Z2 of 3 to some other sequences that come from, say, Fano threefolds or more general Fano manifolds. So Apéry and Fano, for me, already 15 years ago, that was something that I was mixing. And I was very surprised 5 years ago. I was looking again for some idea how he came up with the sequences, and the way how it's explained usually that there's a sequence of integers that satisfies recursion. It's not the way that he originally thought. And I found some interesting paper by some Indian person who was a stagiaire in Moscow, Nesterenko stagiaire. He was trying to reconstruct Apéry's thinking. And Apéry's thinking was interesting that he had recursion or two-dimensional recursion, not one-dimensional. And then to get the sequence of one-dimensional numbers, he had to go to diagonal. And so when he was asked in Lumini at the presentation of like where does his formula come from, he thought, okay, they come from my garden. I just get them from my garden. People laugh, but this Indian person, he told that in this obituary that I'm showing to you, that he actually explains that his son, he was seeing that that Apéry was studying some tables of Ramanujan. So Ramanujan, he had some 3 interesting continuous fractions, and actually Apéry's approximations, they come from kind of this continuous fraction in Ramanujan's table. So one for Z2 of 3, another for Z2 of 2, and sort of logarithm of 2. And I was originally just interested about this claim that this Indian mathematician, he learned from this obituary about this. So I have read the whole of this obituary. It's very interesting, and I can suggest to everybody to read it. But in particular, I learned that what was his PhD thesis was about. So it was in classical algebraic geometry, as you know. Yeah, so you see that after the war, he had some support from CNRS and so on, some communication with Severia. And then in 78, he did his PhD in algebraic geometry. Is it visible what I'm saying, showing now, right? Or it's better to
it is.
bigger?
I'm always missing what's going on the photo with the birthday party, but
yeah, I'm not sure. That is just his wife threatened to kill him, yeah, something like this. Nothing serious. So that's Paul Dubray and René Garnier was his advisors, and somehow he was related to Godot. And maybe the reason that he was related to Godot is one of the reasons that his work is not so well known, because if you look for MathSciNet, Godot, he has like 666 papers, writing like every month. So probably some French influenced or Belgian algebraic geometry of the time was that so much publishing that people just didn't know what the other people do, because it's impossible to read that many papers. I don't know how you can write it. Yeah, and so somehow it looks that his PhD thesis was not published later and left unnoticed, but what he was about. So we see that his work, original work from 39 to 48, was in the style of Italian algebraic geometry, tradition of Severi and Godot. And in the thesis, he has 3 parts. First part of the thesis, he just writes about foundations of algebraic geometry as they were seen by him in 47. Yeah. Something like pre-Grothendieck, but already post-Weil, you can say. Like Weil and Zariski were already doing something, and he was kind of entering the stream or showing this kind of stuff. He never kind of got interested in schemes, to be honest, because it's not so classical. He was more interested in constructive stuff. So commutative rings and so on. So he proved some theorem about liaison, about of curves, of space curves, that was later generalized by Piskin and Shapiro and others. Generalized from the Radon's result about intersection surface, and look here. Can you see it? Yes, I think.
Yeah, we see a variety of degree.
And constructed a variety of degree 22 in P13, for which the sections are canonical curves of genus 12, in contradiction to a claim of Fano. Yeah. So 5 years ago, sitting in Bonn and being interested more about approximations, I read this phrase, and then of course I'm kind of shocked. And probably everybody now who is in this audience, you recognize what is it. Yeah, it's already in our DNA, this variety of degree 22 in P13. Yeah, and that's his obituary. He was written by his son. I think it's published in 1996, called Roger Apéry, a radical mathematician, 2 years after he died. And at that point, of course, I got very, very agitated. I looked for all maths.net. I did not see any paper of this. Then I see, okay, Francois Apéry, thanks God he's still alive. And I just write to him. Dear Francois, I read in your obituary of your father, like my work is related in this term, but also in other term. And it looks that in his life, I'm kind of connecting things that he did in the beginning of his career with what he did in the end of his career, closing the circle. And kind of constructing, saying that the fruits from Apéry garden, they come from Fano manifolds, but he himself, in his PhD was about classification of Fano manifolds. Yeah, maybe I can stop this, sharing this.
Sorry, I'm missing it. Whose PhD was about classification?
Roger Apéry. This is obituary of Roger Apéry, person who proved that zeta of 3 is irrational. From 39 to 47, he was doing classical Italian algebraic geometry.
But this construction was later, right?
His PhD thesis of 1947, he found variety of degree 22 in P13 that Fano claimed does not exist. That's exactly, literally what's written in his obituary, 1996.
And what's
obituary is written later. You cannot write obituary before the person died. Some people do it, but usually
impractical.
Yeah, so that's an obituary which was written by his son, and his son helps because he was a small child when he was working. He even saw that he was working with Ramanujan tables, something that you cannot read from other sources. Actually, where Apéry got his kind of insight for his 78 paper, it's related to Ramanujan. So you see that today I connect Poincaré, Ramanujan, Iskovsky, Fano, and Apéry. So let me share his this part. Yeah, I think you are seeing it now, but I don't. Oh my. What did I do? Here, yeah. Yeah. So that's the last page of his thesis. Yeah, last page. It's 27 of something. So the first page is titled introduction and so on. That it's third part of his pages. You can see those beautiful tables. And if you're a birational geometer, so I have some sort of course, all of us read the book Iskovskih Prokhorov, Fano threefolds. And let me tell you exactly to which chapter of the book I'm explaining now. It's if you have not, just go and read if you're a student. So Iskovskih Prokhorov's book, section 3.6 or something like this. It's not on this file, so something like section 3. Maybe I need to open some other message. Yeah, Iskovskih is 78, and the textbook that we learn from chapter 4.6, which is called Some Elementary Birational Transformations. Yeah, so this chapter 4.6 that describes elementary birational transformation between Fano threefolds in the style of Fano, Roth, and Iskovskih and others, and that we look for different, as I say, lines or conics or twisted qubits. And Takeuchi seems, yes, I have some written here. So in particular, Takeuchi here in 80s already redone this as a byproduct proving existence of conics and existence of lines. So you need to start the things, you need to prove the existence, and that's what Fano have not touched. And I think Apéry also have not touched. He uses some enumerative geometry of his time, some interesting formula and other things. Yeah, so this table, just if you're a versed in three-dimensional birational geometry, it's the Sarkisov program for Fano threefolds, kind of which, and here you have see 4 lines, this with number 22. These are the lines that Fano missed because he missed this threefold. Yeah, he says, okay, except for Fanos, because I found there's some other thing that you can get, you have also these things. So he was doing, again, the Fano method, repeating this, but looking better and seeing, so he writes, le procès de Fano pour projection from a line, this line, yeah, so give some
Seriously, so it's a paper by Sergey Apéry, right?
Sergey Apéry, this is his PhD thesis. This,
But you said it's 47. Seriously, it's from 41.
Yes,
It's written
this is
41.
41
Yeah.
is written
This is
downstairs.
his PhD thesis, which was defended in 1947.
Yeah, but it's written 41.
Where? Ah,
Below.
yeah.
On the bottom of the page.
So the time when he was either mobilized or hospitalized.
Yeah, sorry. You just don't understand. It's paper which written in 47. That's the way how you
What?
do bibliography in these papers. If you have not read papers from the 40s, you just do them in line, still in 50s and 60s. Doing this bibliography that we do nowadays and that, it's more recent. He just refers to
It's a
Fano's
footnote.
work.
It's a reference footnote. Yeah.
That's a reference from his. I see.
Yeah.
It's not
At
his-
the time, all the references were footnote references. It's a reference to the work of Fano, which you can see here.
I see. Sorry, it was it.
Yes,
And
he
the
says
text
that
was sent to you by his son, right?
Yes. So I write to his son. I say, can you say something more about this? Can I find his PhD thesis? And he says, yeah, it exists in three exemplars. So one of them is in ANS, because in Paris, because he was defended there. So I asked Ilya Ivanberg if he can send me the copy, but he was a bit busy. So another, he says, is at my home, and a bit later I can try to send it to you. And the third copy, guess where is it?
Ленинская библиотека.
No, it's in Princeton because Solomon Lefschetz asked for a copy. So apparently Solomon Lefschetz was very well versed in classical algebraic geometry, one of the best single pieces of work to learn about 19th century algebraic geometry is Lefschetz's works. He describes it very nicely, because you can only there I learned what is actually adjunction formula was meant for brilliant neuter. Yeah, but anyway, so Lefschetz apparently got interested and he knew about this but did not propagate it further. Apéry, after his PhD defense, it's interesting, he went to Italy and he spent some time in Italy and speaking with Italian algebraic geometers, and not a single doc never ever noticed or mentioned in any work of them about this result, that he found a threefold that Fano missed. Yeah. And here, Apéry here explains what was the mistake of the Fano in his language, that Fano, he supposes that the hypersurface that you get is always unicursal, purely unicursal, but for V22, it's elliptic. Have some elliptic thing, rather than ruled. That's kind of his explanation. Yeah, he also says, of course, the 20 does not exist, and so on and so forth. So, yeah, shocking news. I have to finish, but that's the whole point. So, in the standard frame we put about history of classification of Fano threefolds, one name is very undeservedly never noticed, and I suggest to fill the gaps, maybe in the next reprints of Iskovskih Prokhorov book. Certainly, that's a reference that should be there. And yeah, and that's very interesting. For me, was discovery in the history of mathematics that a threefold that Fano missed, so he was found by person who later then found the proof for a proof that Euler missed. So we can also connect Fano and Euler. Yeah, that's it. I'm done. So maybe I can cite from some emails. So yeah, his son, I wrote something to his son with these comments. He told, yeah, thank you very much for putting in the content. Certainly it should be known. I was just too busy for the last 5 years to make it public. That's, I think, the first place where I do it very publicly. I explained it personally for different people, but I found that it's a good moment for workshop organized by Iskovskih Seminar for people to know about this hidden gem of classical algebraic geometry did by Greek French person in 1947, who later became famous for other things. And so my role here is just minuscule, so the distribution of this knowledge, and I'm happy that kind of my work about gamma conjecture, it closes the loops. It relates the end of Apéry's work, his last work, with his first work, closing the circle. So that's it. I'm done. Sorry for smaller time. I have to run soon for them.
Thank you very much. It was amazing.
Yeah.
Any historical questions left? Does he have any explicit comments in his PhD thesis about Mukai-Miura?
No, because his PhD thesis is Fano style, right? So
So he has
And
no
if you
triple
say
projection, right?
Fano Iskovskих, but it's kind of more historically correct will be to call it Fano Apéry Iskovskих classification. Yeah. So in particular, that threefold that Fano missed, Apéry he found it, but nobody cared. Nobody. Neither Fano, who lived for 5 more years after this PhD defense, neither Roth, who lived later and wrote the book. Nobody ever noticed this anywhere.
Yeah, it was while Fano was still
that
alive.
happened. Yeah.
Uh-huh.
And
So
the thing
maybe
is,
you're-
because it looks that they could have even met Iskovskih and Apéry in 78, because, but I think Iskovskih did not really go personally to this. I don't know. And Apéry, he did not know exactly. Because if they will meet, it should have happened somewhere in 78, I think, at least. First, it should have happened in 40s or 50s, and then in 78, like in the better world, maybe they just should meet on the Congress and then say, wow. But yeah, somehow this happened 40, 50, yeah, 50 something years later, but
Great.
Maybe you can also relate
better
to
later
Roth.
than never.
Yes.
Huh?
I said
What?
maybe you can also relate to Roth.
To Roth? Well, I talked about Roth. He wrote this book, and this book, I think, was main reference for Vasily Iskovskih, essentially.
No, I mean with another one.
Another
Also
one.
with yeah, like Apéry was linked with himself. Maybe these two Roths are related in some similar.
Yes, you can say yes. And with Baker and with others, yeah, but already we relate to Euler, right? Yeah, so sorry for no new mathematics, but this was sufficiently shocking for me to learn this history of mathematics. As a student of Iskovskih, I just was, wow.
Okay, great. It was really a very impressive talk with very new information. So let's thank Sergey.
Well, you can see this nice table. I have a new table. Maybe the message is funny that Fano Apéry Iskovskih method of classification of Fano threefolds and another modular forms method of Goloshev, they're completely complementary to each other. And this means that this birational geometry method, it tells us something completely crazy about modular forms in the style of Moonshine, another way around. So there's still something that I'm looking for in Fano threefolds. The story of Fano threefolds is not that close as we think it is. After looking at this table, I kind of, yeah, but.
I have a question. So people sometimes put the slides of their talk on the website of webpage of the conference, and
I can send you my.
Ask the son of Apéry, maybe not the slides, but can you ask the son of Apéry if we can put the thesis on the webpage of the conference?
Yeah, so he wants to publish it somewhere. I think that was his idea, but I'm not sure where you can publish it.
But can we just put it as in the place where we usually put the slides? Attach it to your talk at the web.
I can attach maybe the things that I have shown, right? This table and the last page, which already shows this kind of stuff. I can copy paste something. The interesting part is the last chapter. It's the 3rd chapter where he speaks about this kind of stuff. You can recognize various formulas that you. Yeah, so that's the formula you can also find in Iskovskih Prokhorov. That's table you can find in Iskovskih Prokhorov book as well. Say Sasha is looking now and he's kind of this number 30, 20, 14. Of course, you know, right? That's Hodge numbers and other enumerative geometry stuff and so on. It's very nice reading. I mean, it's good reading. I can suggest it if his son decides it to be available publicly. I think he wants it to be available, but to be maybe better known. That's the idea. Yeah.
Okay, thank you anyway.
Yeah, so I'll send you at least last 2 pages with this table and with his last thing where he shows this. And yeah, already in 96 it was repeated that he did this, but again, people have not noticed. Neither in 40s, 50s, in 78, neither in 96, but good, better, whatever. How many years it passed from 47? Some many. 76 years later, we can know the truth. Okay, so shall I turn off the thing and just and there's a break for no break.
Great, thank you very much. Thank you very much. Let's thank Sergey again.
Thank you.